our last speaker of the session is Juan Camilo Rodríguez Pérez from National Tsing University. So he will also talk about machine learning in quantum optics. Please.
Thank you so much for your presentation. Well, my work is titled Machine Learning Enhanced Quantum State Tomography, but now with covariance matrix approach. This is related to the research that Professor Juan introduced to you, so maybe I can give you some technical details of this approach. Okay, so at our research group, we are focusing on the generation of different quantum states. It can be single photon, CAD, squeeze state for all the wide applications that we have already discussed. So a fundamental part to make this advancement like real is our ability to accurately reconstruct the information. This is why we want to research on quantum state tomography, because that's the way we can extract precise and complete information of quantum states, so we can manipulate them and use them for any kind of purposes, mainly quantum computing and quantum information science. So I think the question underlying my research is like, can we observe the quantum realm, or how do we observe this? So in quantum mechanics, we have abstract objects living in an infinite dimensional Hilbert space, and we cannot directly interact with that, but in the lab we can create some experimental conditions, defeat the coherence, and generate quantum phenomena. So quantum state tomography is the way we can go and extract this information. So what is the state of the art of this? Traditionally, we have been used maximum likelihood estimation, but in our research group, we proved that machine learning can enhance tomography methods, so we get higher precision and faster estimations. But all these methods struggle at describing high-dimensional Hilbert spaces. I would like to introduce an idea that can help me to deal with this. For example, by talking about an entangled system like two-mode squeeze states. So I propose using covariance matrix as an alternative way to represent quantum state, usually represented in Hilbert space with density matrix. So the goal of my research is to create a function that uses machine learning to take some experimental measurements of single mode squeeze state and output the quantum state given by covariance matrix. I will do this for single mode squeeze state, for which we have experimental measurements, and I can benchmark it, and I will extend this idea for two mode squeeze state, which is is one of the interests in our research group right now. So how is the input of our estimation? So we use models from light detection to generate experimental measurement. For this, briefly, we have the field under study, a squid light, and a high amplitude coherent field, which will amplify the signal. The output of this experiment is the quadrature sequence, which is kind of a statistical sampling of the measurement of one of the quadratures of the electromagnetic field. I want to be able to simulate this in a computer so I can train my machine learning method. Okay, so my method has an advantage. It's like it interacts directly with the symplectic structure of the phase space. So let me define a symplectic manifold as collecting every pair of canonical variables for an n-bosonic system. By keeping this in, let's say, some vector operator, I can measure the commutation relations, and this will be in terms of the symplectic form or symplectic matrix. The purpose of writing this is to compactly write the constraint that my quantum system must fulfill. So in order to respect these constraints, I will define the symplectic group, which is all the set symplectic of transformations that live in variance, my symplectic form. Once I have set these ideas, I can define the covariance matrix as the correlation between every part of canonical variable, and in an analogous way to the phase space representation, to the Hilbert space representation, I get some uncertainty principle for my covariance matrix in terms of the symplectic form. So in this table, just want to compare Hilbert space representation with phase space representation. Just briefly, I want to point out that for Gaussian state, the phase space representation can encapsulate the information of my state few parameters, which is quite convenient for a quantum state reconstruction. So now let's get into the technical ideas of how to reconstruct single mode squeeze states. So this is single mode squeeze operator, and these are the explicit components of the single mode covariance matrix. I want you to notice that these are in terms of the squares of the creation and annihilation operators, which are the terms that the squeeze operator affects. So all these terms will feel squeezing, and the way to better visualize this is the quadrature sequence of a single mode squeeze state, and these are plotted the covariance matrix curves. We can see that they oscillate because they are squeezed, and there is some interesting behavior. There is always a point in which covariance matrix becomes diagonal, explicitly in these black lines. In this point, also the variance in X minimizes, the variance in B maximizes. So I want you to keep this in mind. This is a GIF I want to show you, but this is a PDF. So did you download the video that I got? Yeah, I sent you in the. This is just what's happening in the quadrature sequence as we increase the squeezing level. Just of course the states start to squeeze, so we can reduce the uncertainty in the quadrature, and this is how the covariance matrix curves are generated. And this is what's happening in the Wigner space with the Wigner distribution for this state. How do I do this? Okay. But I have many covariance matrix choices, so I would like to make a right choice over how can I fully, or how can I describe my state. So I will write, let's take advantage of the symplectic structure of the space, and there is some theorems that tell us that we can use symplectic transformations, the ones we already defined, to take my covariance matrix to a standard form. This is standard form for single mode case. It just becomes diagonal. So I will say that my cell will be described as covariance matrix in a standard form together with the phase point in which this occurs. So now let's get into the method. How can I build train my machine learning model? So I need to create a good choice over the states I want to train. So I will squeeze thermal states to account for thermal noise, and also I will add some population of thermal states to account for an non-Gaussian noise, or let's say a multimodal Gaussian noise. I will train a machine learning model that will output the parameters, and at the same time I make that the uncertainty principle is respected. So I can generate physically realistic states, so I can fully describe the information of the state. For those curious about machine learning, I base my architecture in time series data because quadrature sequence looks like time series data. So these are ResNet that can deal with gradient vanishing problem. I train with minimum square error, and as computational resources, I have a very powerful GPU, NVIDIA GeForce RTX 3090. Okay, so we have experimental realization of single mode squeeze states in our lab. So a way to characterize this is, for example, we can extract how degraded is the state by measuring the purity. So here I just have the green dots are experimental descriptions of the purity of these examples, and the black dots are the covariance matrix estimations. And these are the 95% confidence interval bars. Also, I can measure how the squeezing behaves in terms of anti-squeezing. So this is one of the things we want to also do in our lab, is to have very good quality measurements. Actually, our measurements, I think they are very good, and I can estimate with these green dots are experimental measurement, and the black dots are the covariance matrix estimation. Also, as another benchmark, I have the fidelity, and here I'm just comparing fidelity by reconstructing density matrix, how it's traditional, and also by reconstructing covariance matrix. I can get with both very high fidelity levels in my reconstruction. And these are reconstructed example of two, one low squeezing level and another high squeezing level, and just want to show that I can fully reconstruct this information. Okay, one of the best, okay, I would like to make a best choice over my model by including some multimodal noise source. So what I did was including this thermality which takes my state out of Gaussianity. So I test my machine learning model with from 0 to 5%, and I found that by using 1% population, I get a better fitting with this. So my model can show robust to this inclusion of multimodal noise, and here I can add different levels of this multimodal noise to see that high fidelity remains high. Okay, so here I have just finished single mode bar. Now we would like to send it for two mode states. I will go fast because it's already time. So I can also find an alternative way to write the covariance matrix in a standard form. I take advantage of this, and this is just how I explicitly write all the elements for the two mode covariance matrix. Just briefly, I want to point out that the entanglement will be stored in the off-diagonal elements because these are the elements that are squeezed by the two mode squeeze operator. So I will use the superposition quadrature to generate the quadrature sequence. This is just the superposition of the two mode fields. And why I use that? Because they are squeezed because of these components, because the individual terms are not squeezed. So, okay, this is analogous before. As a methodology, in a similar way, I use tensorial product of two modes thermal of single mode thermal state, and I squeeze through my machine learning model and output a full Wigner space. So we don't have experimental measurements, but we have simulations. So as a benchmark to my to this approach, I can measure fidelity, also estimate four-dimensional Hilbert space. So just conclusion: single mode squeeze state can fully reconstruct my information with high fidelity levels, even including noise. And for two mode squeeze state is promising, and we hope it can help us to reconstruct entanglement information. As a prospect, we would like to use real-time quantum state tomography and compare with experimental results. I know everyone of you is hungry, so thank you.
Thank you. In your slides, you have a table to compare the Hilbert space and the phase space. Okay, I wanted to know how do you introduce the phase space? What's the definition for you?
Okay, by phase space, I mean I want to use canonical operators XP to represent one state. So when I will I work in phase space representation. When I'm dealing with two mode states, I will just have x1, e1, x2, p2. Oh. That's what I mean. So covariance matrix has a few components. When we use Hilbert space representation, we need infinite parameters. That's what I mean.
Thank you.
Okay.
Other questions? So I have a question regarding your the uncertainty on the your estimation as a function of squeezing level. So it seems like if you have a higher squeezing level, your uncertainty gets larger, right? So something like this.
Okay.
Fidelity, uncertainty increase, right? So is that just particularly because the experimental is perfection, or?
This is simulation because fidelity just when I'm reconstructing how it looks to what it should be. So when we measure fidelity, is more simulation. So it's like what's the reach of my model to how is the quality of what it reconstructs. The more squeezing level, the more squeezed the state, of course, so it's more complicated to reconstruct, fully reconstruct.
Because by fitting, say, if you want to fit a squeeze state, typically you have a larger squeezing, it's easier to fit. If you don't have much imperfection in your noise in your experiment.
So I don't know why.
Yeah, maybe this is more a numerical thing. Even though you can still see that fidelity is still high, these are like 0.98. So this I think is more due to when we write this, basically the density matrix or the covariance matrix, how we generate this is more complicated than when we write this. So I think this comes from numerical context why this is reduced. Thank you.
Okay, so if no more questions, let's thank our last speaker, and also we conclude this session. Okay.